Hello and welcome to our presentation. My name is Ariel. I'm a research fellow at the Technion, and I will be introducing a novel method for mapping previously unexplored indoor environments using autonomous agents. The remarkable feature of our approach is that the agent is able to accomplish the mapping process in half the path length taken by standard current state-of-the-art methods. What is the secret behind this considerable improvement in efficiency? It is the synergistic use of two machine learning techniques, supervised learning and reinforcement learning. Supervised learning amplifies real-time sensory information gathered by the robot and predicts unseen building structures based on similar cases that were examined during an offline training process. The process of motion planning is based on the reward value of reinforcement learning. This is done to optimize the process of improving the predictions. In simpler words, the agent learns to navigate toward regions that contain a high amount of information, which boosts the predictor performance. Despite the resource-intensive and time-consuming training process that necessitate a comprehensive and sizable datasets, the payoff comes at the end of the training journey. The outcome is an inference that is computationally lean, allowing all operations to be run on board a swap-limited platform. This video illustrates one representative real-world experiment. The bottom left window is the ground truth. It shows a bird's-eye view of the entire structure, which is unknown to the agent a priori and does not exist in the trained dataset. In the bottom center, we see our occupancy grid built upon consecutive frames captured by onboard depth cameras. The window on the bottom right features the enriched map produced by our deep learning-based predictor, which runs fully on board. At a previous ICRA conference, we demonstrated a rapid method to map buildings by using high-quality statistical data related to various structures of tens of thousands of samples. That proof of concept revolved around a simple Python-based environment where we made quite a few relaxation assumptions. However, for real-life drone-based applications, we must account for uncertainty in state estimation and the effect of sensing noise and environmental factors such as furniture that might impact the validity of our predictions. Fast forward to ICRA 2024, and we are excited to present a new model that accounts for all these uncertainties and constraints, followed by a set of experiments that validate our model in the field. All experiments were carried out with a small UPenn Falcon 250 drone that managed to successfully map an office building spanning an area of around 200 square meters and includes a total of 8 rooms. Conflict arises when pairing physical systems with machine learning, especially with resource-intensive simulations. Accurate robotic simulation environments that feature all physical aspects of both the robot and the environment are ideal for validating different robotic algorithms, but fall short when it comes to RL training due to their high fidelity. Their complexity leads to long runtimes, thereby limiting the process of network training, which involves executing numerous scenarios. For this reason, both networks were trained in such a simulation environment that on one hand are low fidelity with fast runtime due to their simplicity, while still being able to fully represent important features such as measurement noise, body dynamics, environmental effects, safety zones, and more. This environment enables the trained agent to mimic the robot's behavior and is efficient enough to facilitate numerous training sessions within a reasonable time frame. Prior to our airborne experiment, we also undertook extensive evaluations in the gazebo simulation environment to validate the applicability of our proposed framework in a wide range of scenarios. Our goal was to achieve an F1 score higher than 0.92, so we can treat the predictor as our observer. Our method was benchmarked against both the current leading and classical exploration algorithms utilizing 4 distinct topologically characterized buildings from the test dataset that were previously unseen. The outcome denotes a 50 to 60% performance enhancement with our method over both the classical and current state-of-the-art methods. Although our framework could run on an onboard CPU or GPU, due to the architecture of our networks, we might also consider running both the networks on an efficient neural processing unit. This would enable us to free up the processor and memory for other calculations and applications, which may not have been possible when relying on other less efficient CPU-based methods. To conclude, in all cases, we managed to map the entire building while following a path half as long compared to results given by a frontier-based approach. This multidisciplinary research involving machine learning, robotics, and control was conducted jointly by the Technion, Hebrew University, and the University of Pennsylvania. Thank you for watching. If the topic interests you, we will be happy to meet you in Japan at the detailed talk during the ICRA conference.